Hello, my name is Brandon Reznicek, and this is my report for Lab 1, Constant Velocity. The purpose of this experiment was to analyze a real-world observation of an object moving at constant velocity, and then compare it to a computer model representing an identical but idealized situation. The observation is represented by a video of a toy car moving across a table at a constant speed and direction, and was analyzed using tracker software. Our computer model was developed using Python and represents an ideal model of constant velocity, which will be used as a comparison to our observed model. We're interested in seeing how similar our real-world example is to our model, and determining the cause of any differences we may observe. The main underlying physics principle in this experiment is Newton's second law. Newton's second law states that the net force acting on an object is equal to the object's mass times the acceleration. We also know that final velocity equals initial velocity plus acceleration times change in time. We can replace acceleration with net force over mass to get the following equation. However, for constant velocity, we know that the net force is equal to 0. Therefore, the final velocity is simply equal to the initial velocity. Why does constant velocity imply zero net force? Well, let's say this is our object, moving at a constant velocity v along the positive x-axis. If the object had a positive net force in the same direction, then that means the acceleration would be positive, which means our object would be accelerating and the velocity would no longer be constant. If the object had a net force in the opposite direction, well, that means the acceleration would be negative, which means our object would be slowing down and it would eventually come to a stop. And if the force would continue, it would start moving and accelerating in the opposite direction. Therefore, for our object to be moving at a constant velocity, a net force of 0 is necessary. Let's take a look at our video. We can upload our video onto the tracker software. We give the program a reference for length, position, and time by adding a length calibration stick, a coordinate system, and indicating the frame rate of our video. This last option tells the program how much time is elapsed between each frame. We use the software to go frame by frame and select where the center of mass of the car is in each frame. The program gives us an output of position versus time. We're only interested in the x position, so we can copy these two columns into Excel. Here's our data in Excel. There are 3 important pieces of information we need to extract from this data in order to model our toy car using Python. The first is the initial velocity. This is calculated by dividing a change in position by the corresponding change in time. The second piece of information we need is the initial position. Finally, we need the value for our final time. Here is the code for our Python model of the motion of our toy car. We used the starter code provided to us, but we needed to add a few pieces of information specific to our model. The first is the mass of our object, which we measured to be 34 grams. The second is the initial position of our object. Next, we have the object's initial velocity. We specified an initial time of 0 and a delta t of 0.01. We set a final time of 0.9 seconds. We set the net force equal to the 0 vector because there is no net force acting on our object. The next line of code is Newton's second law, which is the final velocity equals the initial velocity plus the net force over the mass times delta t. The next line is the object's position. This is equal to the object's position plus the velocity times delta t. Finally, we update the time value by adding on delta t. This is what our code looks like when run. The first part represents the motion of our object. The second part is a plot of position versus time for our model. As we can see, it looks pretty similar to what we got in Tracker. Finally, we get an output of the position versus time values for our Python model. We can now input our data from our Python model onto Excel and plot the position versus time for both our observed motion and our modeled motion onto the same plot. The blue line represents the modeled motion and the red line represents the observed motion. As you can see, the two plots look very similar at the beginning, but diverge quite a bit at the end. The modeled motion has a constant velocity all throughout the experiment, and therefore the curve remains perfectly linear. On the other hand, the observed motion starts curving downward at the end. This means that the observed motion doesn't remain at a constant velocity throughout the experiment, but rather slows down at the end. This decrease in velocity is due to forces that are present in the real world, which we did not account for in our model. Since our toy car was slowing down, that means that the net force acting on our object was not actually 0. There was a net force in the opposite direction acting on our object. This force was due to 2 main reasons: a drag force due to air resistance and friction on the wheels. We could have chosen an object on which drag has a smaller effect. I believe a soccer ball, for example, would have been a better choice of an object. The soccer ball would have only had friction from the air, and therefore would have kept a more constant velocity throughout the experiment. When we analyzed our video using Tracker, we arbitrarily chose the orientation of our axis. If we were to flip the orientation of the axis, then the plot would now have a downward slope onto the negative x direction. The slope and curvature of our graph would remain the same, except negative. While we're assuming a net force of 0 for our model, in real life it's practically impossible to determine how many forces were acting on our object. There are a large number of forces acting on our object, even though some may be insignificant. The gravitational pull from the Earth, from the Sun, from the ruler in the back, the drag from the air and the friction in the wheels, the electric force from the Earth's magnetic field. These are just a few examples of all the forces, and it is virtually impossible to determine them exactly. In conclusion, Newton's second law allows us to construct an idealized model of our motion. For a constant velocity, in the case of our experiment, the net force is equal to 0. As you can see, our model remains linear and maintains a constant velocity throughout. Our observed motion looks like our model at first, but the velocity doesn't remain constant and slows down at the end, mainly due to drag.